So in this video, we are going to look at the basic logic gates that are used in digital electronics to explain the relationship of the inputs that we use to control different parts of a process and how they relate to one another and how they perform certain operations. So with each of these, we're going to look at a few different aspects of each logic gate. We'll look at the symbol of how we represent it in a schematic diagram. We'll look at the mathematical expression, which is called the Boolean expression. We'll look at the table, which it explains how each gate works, and we'll also look at a rule of operation just to kind of help you quickly find what the output is for each of these. Alright, so the first ones we have here. So the first one we're looking at is the AND gate. Alright, so here is the symbol for the AND gate. Pretty easy to remember because the shape of the symbol looks like a D, so AND, D-shaped symbol. Alright, so on the left side we have the inputs, and on the right side we have the output. Okay, and that'll be the standard format for all of these. The inputs will always be on the left and the output on the right. So for this particular gate we have two inputs. For an AND operation we have to have at least two inputs to compare signals to provide an accurate output signal. Alright, so it could be more than that, could be 3, 4, 10, however many you need, but 2 is the minimum. Alright, so we only have one output, and that's going to be the same with every gate as well. So these inputs are labeled A and B, the output is labeled X. There's no real significance in that other than that's how we represent it so that we can put it into the expression to write it out mathematically. But just know that these are real components, so the inputs could be anything. They could be just simple toggle switches, push buttons, any type of control switches or sensors. And same for the output. It could just be a simple LED light, or an incandescent light, or an alarm, or motor, whatever we wanted it to be. Okay, so the letters just represent the real world components. Alright, so the Boolean expression, so that is the mathematical way we represent each of these gates. So for the AND, X equals A times B. Alright, so it's a multiplication operation of these input signals. So if we multiply A times B, that gives us the output. So we can determine that by using this table over here, which we call the truth table. And as I always like to say, it tells the truth, the whole truth, and nothing but the truth. And yes, that's another one of my corny jokes for the day. So we can multiply these values for the inputs to determine what the output will be. Alright, so we have a column for input A, a column for input B, and a column for the output X. So since we only have two inputs, there's only 4 possible combinations that we can have of the different positions that the switches can be. So it's written in binary because that's what the switch condition will be, either on or off, basically. So we represent that with the zeros and ones of the inputs, and we'll do the same for the output. Alright, so the arrangement of these ones and zeros is not just random, it's done numerically. So if we were counting in binary, that's how this is arranged. So 0, 1, 2, 3. So it's always laid out that way in your truth tables. So just keep that in mind as we start expanding these later on, that the layout of the inputs will be done in order. All right, so we can punch this into our expression. So 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is 1. All right, so that is the output operation of the AND. All right, so any switch that's off, anywhere there's a 0, the output is going to be off. So that is my rule of operation. Any low input gives a low output. Okay, or you can just simply shorten that up and say any low gives you a low. All right, so any low or any 0 on the input is going to give you a 0 on the output. So the only time the output is going to be on with this gate is if all the inputs are on. All right, so that's the operation of the AND circuit. All right, so the next one is the OR gate. So the symbol for it, kind of in a arrowhead type shape for the OR. So I kind of remember it as the O for R. This is curved back here. That's my OR gate. So again, my inputs on the left, output on the right. Just like the AND, this one has to have at least 2 inputs to compare for an OR function and 1 output. So the expression for this one will be X equals A plus B. So it's an addition operation. So again, we can use our truth table to determine the output. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 2, which is technically 2 place values, but we only got a single output here. So that one is a 1. Alright, so the operation for this one is any high input gives you a high output. So anywhere there's a 1 in this input section, I'm going to get a 1 on my output. So any high gives a high. Doesn't matter where it's at. So the only time this output is going to be off is if all the inputs are off or a 0. Okay, but if any switch is on, then the output is going to be on. Alright, so that is the function for the OR gate. Alright, so the next one we have is the NOT gate or the inverter. Alright, so with this one, this is the only gate that has a single input. So there's only 1 input and 1 output. Okay, so we use this to invert the signal, basically to change it to the opposite. So the symbol here is a triangle shape with a circle on the output. So that is important to have that. Okay, so that's what makes it an inverter. So there's some other symbols similar to this used in electronics that do other purposes, but this one has the circle here and that makes it an inverter. Alright, so the output here, or the expression X equals A naught, or that sometimes is just written as A equals A naught, because it just takes that signal and makes it the opposite. So we write that in our expression with the line over the top of it. So anytime you see that with the expression, that means we're doing an inverting function. Okay, so it's important to know that as we move to these next gates, how that works. So the line over the letter or group of letters, it means that we're doing an inverting function. Alright, So the truth table for this is really simple because there's only one input. So with binary, there's only two choices, 0 and 1. And because it's an inverter, it gives us the opposite. It's real easy. So a 0 gives us a 1 on the output, and a 1 gives us a 0 on the output. Okay, so here the output is going to be opposite of the input. Okay, so that was real easy to remember. So that's the only gate that has a single input to it, the inverter. All right, so the next one is called the NAND gate. So those are your three basic logic functions. So everything else kind of just derives from these three. All right, so the next one is called the NAND. So that basically means not and. So it's an AND gate with an inverter connected to its output is basically all it is. So the symbol you'll see is basically the same, except we have the circle on the output, and that makes it a NAND. All right, so the expression here is still the same operation, A times B, but we have the invert on the output, so we put a line over that. So it's AB naught. All right, so that needs to be a solid line because we're inverting on the output. So if we had short letters here, or short lines, excuse me, over each of these, that means we are inverting the inputs, and we'll get into that later. So the inverting takes place after the operation, so we put a solid line over all that. All right, so that means that this truth table is going to be the opposite of the AND truth table. So it was 0, 0, 0, 1. Now it's going to be 1, 1, 1, 0. Okay, so we basically still multiply it. 0 times 0 is 0, and then it gets inverted, makes it a 1, and so on. So for this one, here, any low input gives a high output. So any low gives a high. So any switch that's off on the NAND is going to give you a high output operation. Okay, because it's being inverted. So that's why this rule is basically opposite here, where any low gives a low, now any low gives a high. Okay, so it's just reversing that, basically. So that is the NAND operation. All right, so next we have the NOR gate, and it's basically the same as the NAND. So we're taking the basic OR function, and we're adding an inverter to the output to give us a not or function. So the expression is still going to be A plus B, but with a line over it because we're inverting the output. So the truth table is going to be opposite of what the OR is. So it was 0, 1, 1, 1. Now it will be 1, 0, 0, 0. So again, we add these and then invert. So 0 plus 0 is 0. Invert it makes it a 1. So the rule for this one is any high input gives a low output. So any high gives a low. So anytime a switch is on, no matter where it's at, you're going to get a low output on that gate. All right, so that is the NOR function. All right, and then the next one here, or the last two, are what we call our exclusive gates. Okay, so this first one is called the exclusive OR. and it's a little bit different operation. So it's not a common circuit used in digital control. It's really a specific operation. So it's known as a comparison gate to compare signals to see if they are the same or different, basically. All right, so let's just get into the expression and table and then talk about what it's doing here. All right, so it's an exclusive OR. We abbreviate that as just an XOR gate, but that stands for exclusive OR. So the way the symbol is done is that you have this space here on the inputs to an OR gate, and that's what makes it an exclusive OR. So you can see the comparison of just a regular OR and an exclusive OR. All right, so the expression here, X equals A exclusively OR B. All right, so that's how we write it as a Boolean expression. So the operation here, the first part of it is identical to the OR gate. So 0, 0 gives you a 0, 0, 1 gives you a 1, 1, 0 gives you a 1, but the last one is where it changes here. So 1, 1 is going to give you a 0. All right, and that's the exclusive function here. So what this is comparing is to see if the switches are the same or if they're different. So if both switches are a 0, we get a 0. If both switches are a 1, we get a 0. If they're opposite of each other, that's when we get a high output. Okay? So I remember this as like inputs gives a low. Or you could say unlike inputs give you a high, either way. All right, so if the switches are the same, the output is low. If they're opposite, then the output is high. So you could use this where you have two different switches or sensors monitoring something, and as long as they're both in agreement, as long as they're both off or they're both on, then the output is 0 and everything's fine. But for some reason, if one of them was to be off and the other one to be on, so they don't agree, so if they're measuring the same thing but one is getting a different reading from another, then the output becomes a 1. So that could sound an alarm to let us know that there's something wrong with our process. So that's the kind of application this is used for. So it's very specialized. All right, so that is the exclusive OR function. Like inputs give you a low. All right, so this last one here is the exclusive NOR. So it's really just the opposite of this. So the same symbol, except we have the circle here on the output to indicate that it's being inverted. So the expression, as you might expect, will be the same as the exclusive OR, except with a line over it. And the table will be the opposite of the exclusive OR, so it will be 1, 0, 0, 1. So with this one, like inputs give you a high. So just the opposite of the exclusive OR. So if they're the same, you get a high. If they're different, it gives you a 0. Okay, so it can be used in the same type of application that we just talked about for a different purpose. So here, if they're both off or both on, then the output is on. If for some reason they're different, then it gets a 0. So that could be used to turn off the process, to shut it down basically if the switches don't agree. But as long as they agree and they're the same, you get a high and the system is allowed to run. So just a different application there. Okay, so here, like inputs, if they're both 0 or both 1, we get a high output. All right, so that's a basic introduction to the logic functions, the 7 logic gates. So hopefully that gives you a little better understanding of how those work, and we'll be using these a lot more to start to build combination circuit to do a lot more advanced digital logic controls. Okay, so if you got any more questions, see the notes on Blackboard that tell you more details, and you can always contact me for more information. All right, thank you.